All right, we're moving on to a new unit. We have already studied linear functions and we've studied exponential functions, and now we're moving on to a different type of function. So this first part here, the start thinking says, analyze the following functions, determine what family they come from, is it linear or exponential, as well as whether they are increasing or decreasing. So on this first one, I always check for linear first, and you can see that it is increasing by 5 each time. So that one would be linear because there is a common difference of 5. And not only that, but you can see as the x are increasing, the y's are increasing. So I'd say that's an increasing linear function. The next one I check, and I can see that it is multiplying by 2 each time, which means the common ratio is going to be 2. And when you look at that, you know that it is going to be exponential. And the reason why is being multiplied by the same number or as a common ratio. Now the next one, if you look to see if it's linear, first it's adding 3 and then it's subtracting 1. So that is not going to be linear. And when you see if it has the same number you're multiplying by or does it have a common ratio, 11 divided by 8 does not equal 10 divided by 11. So it is not exponential either. So it's neither. It's not exponential nor linear. Now, when you ask yourself whether it is increasing or decreasing, as the x is increasing, you can see first it goes 8 to 11, it's increasing, but then it starts decreasing again. So unlike the functions we've been looking at that are either just increasing or decreasing, this one seems to increase and decrease in the same exact function. Now, our next problem here, which is an application that introduces you to the topic we're talking about, it says Noah has 50 meters of fencing to completely enclose a rectangular garden in his backyard. Draw some different diagrams that might be possible shapes for the rectangle and label what the side lengths would be. So when you do this, one of the ones I thought of could be a 10, 10, 15, 15, because that adds up to be the 50. So a length of 15 and a width of 10. Then I had another one, which was a 1, 1, 24, 24. And another one that was 12.5, 12.5, 12.5, 12.5. Those are 3 different possibilities. And the main thing that I realized here is that even though you had 50 meters of fencing, the length and the width could only add up to be half of that because you're going to end up doubling the length and doubling the width to talk about the perimeter. The next question says, find the length and width such that the rectangle would produce the largest possible area, because that's the goal. You'd want to have the largest garden. Now, what I started doing was just testing numbers. I said, what about 1 and 24? That gives you 24 for the area. So then I went bigger, 2 and 23. That adds to be 25 for the length and the width, and you end up getting a bigger area of 46. So I was like, okay, let's just keep going. I went to 3 and 22. It got bigger, 10. I said, I'm going to jump a bunch. So I skipped 4, 5, 6, 7, 8, and I went to 10 and 15. 10 and 15 gets you 150. I was like, that's even bigger. Then I went to 11 and 14, and that gets you 154. And I was like, that's awesome. So I went to 12 and 13, and that was 156. And I was like, okay, well, 13 times 12 must be even bigger. And when I did 12 times 13, you ended up with 156. And 14 times 11, the area starts decreasing at that point. So it's kind of like the function we just looked at the table for. It's increasing for a while, and then it starts decreasing. I found that it was somewhere between 12 and 13 and 13 and 12. So I made a guess that maybe it's in the middle of that, and I tried 12.5 by 12.5, and I did get slightly bigger than 156, and that was your sweet spot, was 12.5 by 12.5. And what we found out here was that a square is the best rectangle to maximize your area. As you push it more towards what you would generally think of as a rectangle, where not all the sides are congruent, you would end up getting something that would have a smaller area. And if you say a square is not a rectangle, the only thing it needs to be a rectangle is a 4-sided figure with a right angle, which it has. So a square is a rectangle. So now we're moving on to what the graph might look like. So I went over and I picked out some different lengths, 3, 8, 12.5, 14, 20, and 21. And I figured out what the resulting width would have been, and I multiplied them to find the area. But we're supposed to be plotting the points that represent what a length could possibly be and what the corresponding area. And repeatedly, I kept accidentally graphing like 322 rather than 366, and 817 rather than graphing 8136. So like I said here, ignore this column for the graph. It is going to be a length relating the length to the area. When I graph this, you can see that this does not look like a line and it does not look like an exponential. This looks like some kind of a U. And the name, at this point in the lesson, I explained to students that this type of function was called a quadratic. Now, a quadratic, when you're looking at the graph, is going to look like a U, which is also called a parabola, opening upwards or downwards. Okay, so this one would be some weird curve, which is the actual name is a parabola, and this is what the new type of function we're studying this unit, which is called a quadratic. So let's keep on moving on. The other thing we could look at here, I at the bottom of the table, I said if you had a length of L, then the resulting width would just be whatever's left over from the 25. So it'd be 25 minus L, and the area would be L times 25 minus L. And when you look at that, you end up getting L times 25, which is 25L, and then you have L squared. So then that's a plus, not a multiplication inside of those parentheses. So that brought us to the next thing. What does a quadratic look like as an equation? And the rule is if you're dealing with x's, the highest degree of x would be x squared. You won't have x cubed, but you will have an x squared in there. You might also have something with a term with just an x, but the highest will be an x squared. So far, this thing that we are calling a quadratic function will look like a U, either opening upwards or downwards. And not only that, but the highest degree when you're looking at the equation will be an x squared, or in this case, it was L squared, and that's why it's quadratic. Now, when we move on to this, they give us two different situations. You have pattern 1, pattern 2, and you were supposed to be making a table of the resulting number of dots depending on what step it is for each one of them. And then you're trying to figure out how many there would be at a certain step. So the way that I decided to do this was I like writing equations, because once you have the equation, you can just substitute in a number for any step level and then go from there. So the first one, I got that information, I made the table. You can see the table right next to the diagram with all the dots. And I got 0, 1, 1, 3, 2, 5, and 3, 7. When you look at this, you see that it is linear because it would have the common difference. You're always going to be adding 2 each time. Not only that, but I know my equation has to be y equals 2x because the rate of change is 2. And that does not work because 2 times 0 is 0, but I'm supposed to get a 1. 2 times 1 is 2, and I'm supposed to get a 3. 2 times 2 is 4, I'm supposed to get a 5. So we found out that we still needed to add 1 to it. Now the next one, when you're looking at that table, you get 0, 0, 1, 1, 2, 4, and 3, 9. When you look at this, it ends up being a quadratic. And the reason it's a quadratic, take a look down below where it says 2. The first one you can see, I made the table, and the table was linear for the first pattern, and the difference is always plus 2. So the difference is plus 2, we know it's linear. Now I want to show you with a table how to find out if something's quadratic. If you try to look for a common difference, you could see the first time I did that, it was plus 1, plus 3, plus 5, plus 7. They're not the same, so it's not linear. But if you do it one more time and it does become the same, then that's called a quadratic. So since going from 1 to 3 is plus 2, 3 to 5 is plus 2, 5 to 7 is plus 2, since that is true and the second difference is the same, then that would be a quadratic. So we know that pattern number 2 is quadratic, and why that was handy is I know it needs to have an x squared in there. So if I wanted to write the equation, it's going to have an x squared. So you start out just saying, is it just y equals x squared? And it is, because 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. And the beauty of having this is that you can go over and just substitute a value in to find out how many dots there'd be. So for 5, you could see that when you substitute a 5 into your equation for the linear one, you get 11. And when you substitute a 5 into the quadratic, you get 25. So putting this all together, we know that a quadratic is going to have the highest degree of degree 2, meaning it's going to have an x squared in there. It might have lower than that, but it won't have higher. So you might have like x squared plus 5x plus 3, where you have terms with lower degree, but you will not have anything higher. We know that if you look at the table, the second difference is going to be the same. So the first time you try to find out the difference, it's not the same because it's not linear, but if you do it again, it will be the same. And then we talked about the graph looking like a U. So this last part right here, when we're looking at the graph, I plotted all the points for pattern 1, and you could see it goes along with what we thought it was, linear, it's a line. And when I graph the other ones, it has this curve. The only funny thing here is that it doesn't look like a U because it looks more like an exponential curve. The reason why that is because we didn't go into the negatives. If you use the same equation and went into the negatives, it would pop up to be a U rather than flattening out like an exponential. But you got to be careful when you're only looking at part of a graph and trying to make a generalization of whether it's quadratic or exponential, because you can't see the whole thing and you can't see if it's a U or if it's like one of those plane taking off type things. Explain why graph number 2 pattern looks the way it does. It's a quadratic, and it's supposed to look like a parabola, but we're only looking at half of it. Okay, let's go on to the homework now. In the homework, the first one is talking about a situation just like the one we did in the notes, but in this case, it's saying the perimeter is going to be 20. So we know the length and the width together have to add to be 10, because you're going to double the length, double the width when you're talking about perimeter. So that's how I got those other numbers, and I multiplied them together to find the area. It says, without calculating, predict whether the area of the rectangle will be greater or less than 25 square meters if the length is 5.5 meters. So if you get a 5.5, then the other one is going to be 4.75. So 5.5 times 4.75. We know that the 5.25 times 4.75 is going to get 24.9. Now, I know it said don't go over and do your calculations, but the calculations say that it's less than 25. And the reason I know that it's going to be less than 25 is because we know that having the square is going to give us the biggest area, and the square would have been a 5 by 5. So anything other than a 5 by 5 is going to give us a smaller area. Next, C, did the values change in a linear way? They do not. Did they change in an exponential way? They do not. There's not a common difference, and there's not a common ratio. This is changing in a different way, which we know is called quadratic. The next one here says, which of the statements best describes the relationship between a rectangle side length and the area as represented in the graph? And the answer is C. As the side length increases by 1, the area does not increase or decrease by an equal amount. And that's because we're talking about trying to figure out if it is modeled by a linear. So it's going to be C is your answer. On this one right here, number 3, explain why the following is not linear or exponential. If you look at the first difference, they are not the same. When you look at the ratios, they're not the same. So since it doesn't have a common ratio, doesn't have a common difference, it's not going to be linear. If you went over and took this, if this was quadratic, if you did the second difference, so this is going to be minus 2, minus 2, minus 2. Since the second difference is going to be minus 2, we know this thing has to be quadratic. I had the students skip this problem right here. It's not in your notes, and we're looking at this last one. On this last one, when we're looking at this, I can already see that when I make it into a table and I check, it is going to be linear. And it's going to be linear, and it's going to be y equals 4x because the rate of change is 4, and I did not have to add anything to it because 4 times 0 is 0, 4 times 1 is 4, 4 times 2 is 8. So I knew the equation was y equals 4x if you're using x's and y's. And when we substitute in a 4, you are going to get 4 times 4, which is 16. Now the other one is going to be a quadratic. The way that I knew that was if you make the table, the second difference ends up being the same. Now, when I looked at this, it looked like there was always that 2 at the bottom. So that had to be there always. And the other one did seem like it was always being created by the number of steps squared. 0 squared gave me 0 dots above the 2. 1 squared is 1 dot above the 2. 2 squared is 4, which is 4 above the 2. So I knew that there was the n squared, but then it constantly had the 2 there. So I said plus 2. And once I had that, I was able to substitute in a 4. And 4 squared is 16 plus 2 is 18. And then lastly, which pattern shows a quadratic? You can see that I took the table. I saw that the first difference was not the same, but the second difference was the same. It became plus 2. So the second one would be the quadratic. If you graphed it, you would get a nice U either opening up or down. All right, that is opening up our study of quadratics, which is huge in Algebra 1. I think we actually do 2 units on quadratics. So let me know if you have any questions. Thanks for watching. Bye.